Hello guys, in this video we're going to talk about the Taylor series. I actually recorded this video and just lost the soundtrack of it, so it is my second time to record this video. So the Taylor series is saying that a function can be written as a form of an expansion of this. So it is telling us that we can approximate the value of fx by just plugging number of a certain value, such as like when x is equal to b, we can plug into this function and find the value of fx or fb. And how it works is that for now we're just taking a look at the first two terms. For the first two terms, it is saying that the value can be approximated by a straight line. And this is a slope at this specific point, so this function describes this line. But this value is quite often when we go like to this value, c, when approximate this, the value is not very close. So to get a better result, we're just plussing this term, plussing more terms such as this, and plus eventually there will be very little difference between the real value and the approximate value. And if this term is just when n is approaching infinity, there actually is no different from the original function. So for now, we're going to prove the Taylor series. The way we prove Taylor series is just using that. Actually, this is a definition of the integral. So this is going to equal to fx minus f0. And we have fx is equal to f0 plus x f prime t and changing t. For now, we need to prove another stuff, which is called fx f prime t x minus t dt is equal to this. They're actually identical, and we're going to see it. In this case, we're just treating x as a constant, or we can write out as this form if you like to, so it won't confuse you that much. Here we go. For this part, it is just evaluating the area under this curve from t equals to 0 and to t equals to a, and t equal to 0 is just evaluating the curve, the area under this curve. And for this term, it is actually doing the reverse process. We can see it by just plugging numbers such as t equal to 0. We can see it is equal to f, and this one is a. It is at this point. So when t is equal to a, it is at this point. So when t is increasing, this function is just pushing this word, like leftward. So this actually means that it is evaluating the area. It is just going to be the reverse, the reverse way of finding the area under the curve. And now we're just moving on. So this one is equal to f0 plus this f prime a minus c dt, and in this case a is equal to x. And for u substitution, we use that u is equal to 1, and actually, let me think, nope. dv is equal to dt times 1, and u is equal to f and this. So du is equal to f x minus t dt. Why is there a negative sign? You may ask. It is because the chain rule, and there's a negative sign over here. So when taking the I'll just write it out. It's better this way. X minus c dt, and this by the chain rule is evaluating this dx minus t times dx minus t dt, and this term is equal to -1. Pretty nice. And now we have this term is equal to, just writing out this term, u is this x minus t, and v is equal to t from 0 to x. And because there's a negative sign and there's negative sign, we'll just write it out. It's better this way. F x minus t dt and times t. So the negative signs cancel each other out, just leaving the positive sign over here. And similarly, we can use substitution, and using dv is equal to t dt, and u is equal to f double prime of x minus t. So du is going to be f triple prime minus x minus t dt. This is going to t squared divided by 2. And now we're taking a look at this. This is just going to be, when plugging x, this term is going to be f 0 times x. And when plugging 0, this term is just going to be 0. Because when t is equal to 0, this term is equal to 0. And for this term, this is just going to be u x minus t times v from 0 to x plus, because there's negative sign over here, so it cancels each other out. This is equal to this. T squared 2. And so on. We can see the formula is just get into this form. Let's get into this form. Because there's oh my god, what I'm doing. There's 2 over here, and we know that xn dx is equal to xn plus 1, n plus 1, and when we do that, it is just going to be, this term is just going to 2 times 3 times 4 times 5 blah blah blah, and it is just equal to the n factorial. And so now we prove this theorem. The Taylor series is just equal to this term. So now we're taking a look at the cosine x, and how can we do this? The formula is given over here, and when you plug in the value of 0, it's just going to be 1. And when you take the derivative of cosine, it's just equal to a negative sign. And when you plug in 0, it's going to be 0. And double prime just negative cosine x, which is equal to -1. And triple prime is just going to be 0. So the cycle, and we take 4 derivatives, it is just going to be the reverse, just similar to the first step, which is equal to sine. So you can see there's a cycle here. So the term is just going to be, the first term is 1, and oh my god, wait a second. Yes. 1 minus x squared divided by 2 plus x4 divided by 4 factorial, and so on. Yes. And now we're going to take a look at sine. Similarly, we can see a cycle over here. So the first term is going to be 0 plus 1 times x divided by 1 factorial plus 0 minus 1 times x cubed to the 3 factorial, and so on. We can see the pattern here, so which is equal to this. And now we're going to take a look at the Taylor expansion of this function. So similarly, we can write out like, I'll just write the first few terms. f0 is just going to be 0, and f is equal to this. And we plug in, it is going to just be 1, and f double prime is this. And we're plugging in the -1. Triple prime is just going to be 2, 1 plus 3, which is 2, and so on, so on. You're just going to be this term. And now you may wonder, what is the blue part for? So the blue part is just saying that for certain value, the Taylor series works, but for like if x is greater or lesser than a specific value, the Taylor expansion is not going to work because the series is divergent. What I mean by divergent is that the series is just going to be infinity or to negative infinity, or just not approaching a value at all. So now we're going to take a look at the radius of convergent. This part is not required, but it is kind of important in calculus species. You can listen to it if you want. So there's a theorem here. So when an plus 1 divided by n, and this is an absolute value sign. So this is equal to rho. If rho is lesser than 1, it's going to be convergent, and if this rho is equal to 1, is the series is inconclusive. When rho is greater than 1, it is divergent. So the way we prove this is just going to be really simple. We can take a look. An plus 1, an rho. Yeah, you can see that. And for convenient purpose, we're just considered in the case where all an is equal is greater than 0. For if an is less than 1, you can take a you can search it up and learn it on your own. I'm not teaching it here. So you can write it out as an plus 1 and rho an. And so on. You can an plus 2 is equal to rho squared an. And an plus 3 is rho 3 an. And there's a formula for this one. Just the first term is this an 1 minus rho, just for, in this case, just write it as m, because there's m terms. And 1 minus rho will limit m is approaching infinity. If rho is lesser than 1, this term is just going to be 0. So the series is going to be convergent to a number. So when rho is equal to 1, this is kind of weird. So it is inconclusive. So when rho is greater than 1, this term is just getting to infinity. So the series is convergent. And now we're moving on to consider the radius convergent of cosine x. So we know that cosine x is equal to this term. So the term for an is this, and when we divide this and by this, you can see it is equal to this. And for all value of x, this term is just going to be approaching 0, because when n is getting very, very large or approaching infinity, this term is always going to be 0, so which is lesser than 1. So for all value of x, we can see that the Taylor expansion is going to work. And why Taylor series is useful is that it is good for solving equations and approximating values. When the calculator is finding values such as sine of 80.02 degree, it is just going to plug in the number to the Taylor series and find the value. The Taylor series of sine x is here. And it is also for solving equations such as this stuff. It is really difficult to solve it by just guessing solutions. Yeah, it's actually not that bad. The guess we have here is that the value of y can be written out as a Taylor expansion, and for the radius is equal to 1. And when we plug in this value, we can find that there's a term for this. And when we plug in, we can find the value of yx is going to be this. And so we're done with this lesson.